Start with this. Right now, as you sit there staring at your screen, an invisible storm of pure energy is exploding all around you in every direction at once. Billions upon billions of tiny packets of light are racing through the air, slamming into your eyes, bouncing off your skin, passing straight through the walls, and even zipping through your own body without ever touching or interfering with each other. It's total chaos, yet somehow you see a perfectly sharp picture of the world. How is that even possible? And that's just the visible stuff. Right now, radio waves from stations hundreds of miles away are pouring through your room. Your phone is chatting with cell towers using the same kind of energy. Heat is radiating off your skin, and cosmic rays from exploding stars billions of years ago are slicing through everything. All of its same stuff as light, just different flavors. If your brain isn't already spinning, it's cheeky with me, because we're about to rip the curtain off what light actually is. And once you see it, the everyday world will never look ordinary again. If you love having your mind blown by the true beauty of reality, smash that subscribe button right now. FM, AM, satellite radio, Wi-Fi from your router, Bluetooth to your headphones. 5G from your phone of it is light, exactly the same kind of light your eyes see, just stretched out too much longer wavelength. Those waves can pass through walls, because the longer the wave, the less it cares about small obstacles like drywall. If you want proof, they're really there. Just turn on a radio. The moment you tune it, you pull one specific station out of the invisible soup that was already filling the room. Nothing new arrived. You just gave your antenna the right rhythm to listen to what was already passing through. Go the other direction, shorter waves in, you hit ultraviolet. The stuff that gives you a sunburn and lets bees see patterns on flowers that look plain white to us. Shorter still, X-rays. Hospitals use them to look straight through your soft tissue and see your bones, because those super short waves slip between atoms that block visible light. Even shorter, gamma rays from radioactive materials and exploding stars billions of light years away, zipping through the entire planet as if it weren't even there. All of it's radio, microwave, infrared, visible, ultraviolet, X-ray gammas, exactly the same phenomenon. The only difference is how fast the electric and magnetic fields wiggle. Same speed, same rules, different frequency. And every single flavor is pouring through the exact same space at the exact same time right now, without interfering. For hundreds of years, the greatest minds on Earth argued about what this stuff actually is. One side said light is made of tiny particles like invisible bullets fired out in straight lines. That explains shadows and why light doesn't curve around corners. The other side said no, it's waves, like sound or water ripples, spreading out and bending and interfering. Both ideas had evidence. The argument lasted 2 centuries. Then came the double-slit experiment that seemed to settle it once and for all. Shine light through 2 narrow slits onto a screen behind them. If light were particles, you'd expect 2 bright lines on the screen, one for each slit. But that's not what happens. You get a whole series of bright and dark bands, exactly what waves do when they overlap. Crest meets crest and you get extra brightness. Crest meets trough and they cancel to darkness. So light had to be a wave. End of story. Except it wasn't. Scientists eventually built detectors sensitive enough to catch light one tiny packet at a time. And guess what? The detector clicked like a tiny bullet hitting it. Particle behavior. But when they sent those single packets through the double slits one by one, over time the exact same interference pattern built up on the screen. Each individual packet somehow behaved like a wave that went through both slits at once and interfered with itself. Mind officially blown. So, which is its wave or particle? The real answer is neither, and both, and something we don't have a perfect everyday word for. Light is light. What we call photons are real. You can count them. Your phone camera sensor literally counts photons to make every picture. But these photons don't travel like little marbles. They explore every possible path from source to detector at the same time, like waves spreading out in every direction. When you try to force the question, which slit did it go through, by measuring it, the wave behavior vanishes and you get straight particle clicks. The act of asking a particle-style question forces a particle-style answer. The photon isn't changing what it is. It's always a quantum object. We're just choosing different ways to look at it. This quantum strangeness leads to one of the most beautiful ideas in all of physics. Light always takes the path that gets it from A to B in the least possible time. It's called Fermat's principle, and it's been around since the 1600s, but its consequences are still. In empty air, the fastest path is a straight line obvious. When light hits a mirror, The angle it bounces off is exactly the one that makes the total travel time shortest. You can prove it with high school geometry. When light goes from air into water or glass, it bends. Why? Because it slows down in the denser stuff. To minimize total time, it actually travels farther in the fast medium air and takes a shortcut through the slow medium water. That bending is called refraction, and it's why a straw looks broken when you stick it in a glass of water. The same rule explains why you see mirages on hot highways. The air right above the scorching pavement is thinner and faster for light than the cooler air above it. So light from the sky curves down into that fast layer, speeds up, then curves back up to your eye. Your brain assumes light travels in straight lines and tells you there is water on the road. But it's really just a reflection of the sky. Even the sunset you watch every evening is an optical illusion caused by the same principle. When the sun is right on the horizon, it is already dipped below the edge of the earth. But Earth's atmosphere gets denser toward the ground, slowing light down. So rays from the sun curve gently through the atmosphere, staying in the faster upper layers longer before bending down to reach your eye. You're literally seeing a ghost of the sun that is already set. Now let's build something useful with this idea. Want to focus light from a distant star onto one tiny spot so you can study it? You need every possible ray, whether it hits the center or the edge of your telescope, to arrive at the same time. A curved mirror shaped like a parabola does exactly that. Every path, no matter where it hits, takes the identical total travel time to the focus. That's why giant telescopes like the one at Palomar use parabolic mirrors. Lenses work the same way, but with glass instead of reflection. Glass slows light down. So by making the lens thicker in the middle, you add exactly the right delay to the straight-through rays so they match the time of the rays that take longer side paths. All rays arrive together, boom. Perfect focus. Eyeglasses, microscopes, cameras. Binoculars, every optical device on Earth, is just a clever way of equalizing travel times, so light does what we want. But here is the deepest mystery. How does light know which path is the fastest before it even starts moving? Does it somehow scout every possibility in advance? In a way, yes, and that's where the quantum picture gets gorgeous. Think about radio waves for a moment. They're easier to picture because their wavelengths are centimeters long instead of millionths of an inch. Set up a radio transmitter, a detector, and a wide metal slit between them. The waves go through just fine. Now move the detector off to the side with a wide slit. Almost no signal reaches it. Why? Because the waves are checking nearby paths, and those paths take slightly different times. The little arrows we use to describe each path point in different directions and mostly cancel each other out. But if you squeeze the slit down to almost nothing, suddenly the sideways detector starts picking up more signal with only one path available. There's nothing to cancel against. Same thing happens with visible light. Hold two fingers almost touching in front of your eye and look at a distant streetlight through the tiny gap. The light stretches into a line with colored bands on the edges. That S light refusing to travel in perfectly straight lines because it is checking nearby paths and interfering with itself. You're watching wave behavior with your own eyes. The modern quantum explanation ties everything together in one breathtaking framework. Every photon really does take every possible path at the same time. For each path, we draw a little arrow whose direction depends on how long the path takes. Arrows for paths near the shortest time route all point roughly the same way and add up strongly. Paths far from the shortest time have arrows spinning all over the place and cancel themselves out in beautiful spirals. Almost all the probability of the photon showing up comes from the tiny cluster of paths right around the fastest route. That's why light appears to follow straight lines in Fermat S principle, even though it is actually exploring everything. The wasteful paths simply interfere themselves into nothingness. This single idea summing arrows for every possible path connects the particle clicks we measure with the smooth wave behavior we see in everyday life. It explains why covering part of a Miradosan T destroyed the reflection. You're just trimming the unimportant outer spirals. The central cluster still does all the work. It is the bridge between the quantum world and the classical optics we use to build telescopes and microscopes. And remember, all of this is happening across every wavelength at once. Radio waves meters long carry music and news from the other side of the planet. Microwaves centimeters long heat your food by making water molecules spin. Infrared micrometers long warms your skin and lets night vision goggles see in total darkness. Visible light only 400 to 700 nanometers paints the world in color for our eyes. Ultraviolet, shorter than that, triggers vitamin D production but also DNA damage if you get too much. X-rays slip through flesh to reveal broken bones. Gamma rays, the shortest and most energetic, come from nuclear reactions and distant cosmic explosions. Every one of these is an electromagnetic wave electric field wiggling up and down, magnetic field wiggling side to side, marching forward together at 186,000 miles per second. The longer the wave, the easier it slips through matter. The shorter the wave, the more it interacts with atoms. That's why your Wi-Fi signal goes through walls, but visible light bounces off them. Why doctors can X-ray your hand, but not see it with your eyes. Yet all these different waves coexist in the exact same space without disturbing one another. They simply pass through like ghosts. Stop and really feel that for a second. Right now, inside your body, there are radio waves from a station in another city, infrared waves from the person sitting next to you, visible light from your screen, ultraviolet from the sun outside, and cosmic gamma rays from events that happened before humans existed, all occupying the same cubic inch of space at the same time. It's the most crowded, busiest, most information-rich environment imaginable. And yet we can tune a radio and hear only one station, look up and see only the sky, or flip on an X-ray machine and see only bones. Our technology and our biology let us cherry pick exactly the slice of this invisible ocean we want. We evolved to understand rocks, trees, and running. Animals, things we could touch and throw. Light is none of those things. It is something far stranger. A quantum object that behaves like a particle when we measure it and like a spreading wave when we dawn. TI. It explores every possible route simultaneously. Yet only the fastest routes survive the interference math. It bends around corners when it feels like it slows down or speeds up depending on the medium, and carries information from the edge of the observable universe straight into your brain. When you truly internalize what's happening, the world transforms. That ordinary sunlight on your wall isn't just bright. It's a stream of photons that left the sun 8 minutes ago, each one having taken every possible path through space. Most of them canceling out so that only the straight line survivors reach you. The radio song in your car is the same story on a different scale. The heat you feel from a campfire is the same story again. Everything you see, feel, and communicate with is just different notes played on the single instrument of electromagnetic radiation. This is what physics is really about, not memorizing formulas, but expanding your intuition until the universe's deepest truths feel as natural as breathing. Once you see light for what it actually is, you walk through life with a permanent sense of air. The air around you stops being empty and becomes an ocean of information, a symphony of vibrations carrying stories from every corner of reality straight to your senses. If this journey through the invisible ocean of light has shifted the way you look at the world even a little, do 3 things for me right now. First, hit that like button so more people can discover this mind-expanding stuff. Second, drop a comment and tell me, what part blew your mind the most? The double-slit experiment, the path of least time idea, or the fact that radio waves and X-rays are literally the same thing as the light you're re-seeing. I read every single comment. And third, if you're not already subscribed, click that button and turn on the bell. We've got more deep dives, coming quantum entanglement, black holes, the true nature of time, man. You're not going to want to miss a single one. Thanks for spending this time with me. Now, go look around the room again, and this time really see the invisible storm that's always been there. The universe is way strange at end, way more beautiful than it first appears. I'll see you in the next video. Stay curious.